stability of bioreactors, and we will continue from where we left. So, what we did was we looked at this model of the chemostat for any generalized form of the specific growth rate mu. If you go back to your notes, you will see, and then we looked at that, and we looked at the steady state for that, and we derived the criteria using Hurwitz criteria. We derived the criteria for the stability of the states. Okay, and then the last thing in the last 5 minutes or 10 minutes of the lecture, what we did was we put in our form without still in the form of the specific growth rates being mu here, as you see on the screen now, and we derived the matrix, because we had so using the Hurwitz criteria we had to derive the matrix A, and then we had to look at the terms of the matrix, and there are some couple of criteria. One is that the two of the terms have to be greater, and then the product of the other two less than 0. So, that was the criteria. So, using that, if you look here, we did this, and I am just going to quickly go through this. This is the last thing I remember having done. So, f1, f2, let us go back and show you what f1, f2 are my two functions. Sorry, yeah. So, f1, f2 are my two functions out here, which represent the balance equation for the cell and the substrate respectively. So, f1 represents the balance equation for the cell, and f2 represents the balance equation for the substrate. So, what we did was we took the matrix A, which was del f1 del x, del f1 del s, del f2 at del x, del f2 del s, and we obtained the four terms A1, A11, A12, A21, A22. So, A11 is this, A12 is this one, A21 is this, and A22 is this one, right. Now, next we go and apply our criteria. So, this is my matrix, and so this is how it looks. Now, for it to be stable, so this is my this A, and A minus lambda gives my is a characteristic equation, will give the characteristic equation for the eigenvalues, which is this. So, this is a characteristic equation. Now, when I arrange them in terms of increasing decreasing lambda powers, this is what I get, and my B1 is this and B2 is this. So, my criteria was that B1 has to be greater than 0, I believe, greater than 0, and B2 has to be greater than 0 too. Okay. So, this is my criteria. So, if you go back, this is my characteristic equation, and the necessary criteria for the roots to be real parts of the roots to be negative is that both the coefficients have to be greater than 0. So, that is all I need to satisfy, fine, B1 and B2. Okay. So, actually strictly speaking, it is this B1 B2 minus B3, but B3 is 0 out here because it is a 2 by 2 matrix. So, for a 2 by 2 matrix, and what I told you is that one of the things is that most of the equations that I am going to give you or you are going to do in the chemostat are 2 by 2 matrices. So, it kind of simplifies your life. All you need to do is look at the characteristic equation for lambda, and then say that the two coefficients of the characteristic equation, one for lambda to the power 1 and the other for lambda to the power 0, they both have to be positive. So, if both the coefficients are positive, then it is straightforward, ensure that the roots have real negative parts, and intuitively also you can realize this. If the coefficients are positive, then obviously the roots are going to be negative. Similarly, if both the coefficients are negative, then the roots are going to be positive. So, if both the coefficients are positive, then the roots are negative. That is all you need to remember out here. So, anytime we do this, the easiest way is to create the characteristic equation for lambda, write the characteristic equation. I mean, you can go the Hurwitz way also, but I find it lot easier to actually be able to write the characteristic. You feel a lot more confident about it to be able to write the characteristic equation for lambda, and then equate the rather the two coefficients to be greater than 0. So, that is it. So, next what we do is we now use the monod growth model. Till now we had been using a generalized value of mu. Now, we use the monod growth model, because unless we use the monod growth model or any other growth model, we cannot come up with a specific criteria. So, the monod growth model, everything else remains the same, remember. So, all the analysis that we did till now is valid for all kinds of growth models, okay, provided it is just a 2 equation system. So, here mu for the monod growth model is given by mu max s over k s plus s, and so del mu del s is given as mu max k s over k s plus s square. So, as you can see straight away over here, del mu del s is greater than 0 for these are things that we have to quickly figure out. So, del mu del S is greater than 0 for all values of S, okay, because its Ks is positive, mu max is positive, and it is a positive number in the denominator. So, it is greater than 0 for all values of X S. So, in the previous analysis we have shown already in the when we did the steady state analysis that here what you see on the screen S naught is less than dKs over mu max plus d. If that is the case, then the reaction does not happen at all. Why does the reaction not happen at all? Because there is not enough substrate for the reaction to happen, physically speaking, and mathematically what you found was that you got a unfeasible or a trivial solution, right. So, if only the Recode criteria, if you remember, go back and remember, was S naught greater than dKs over mu max minus d, okay, and mu max had to be greater than d. Why is mu max had to be greater than d? Because one of the criteria for steady state was mu max equals d, right. The steady state criteria was mu max equals d. Now, if mu max equals d, sorry, mu equals d, I am sorry, mu equals d. Now, mu equals mu max times some number which is less than 1. So, obviously, then mu max has to be greater than d, right. So, then the denominator is positive out here, but the reaction can only happen if S naught is greater than dKs over mu max plus dK. So, we will consider that case only here, because there is no point considering the other cases, and if you need I will go back and show you the chart we had. We had a nice chart which showed, yeah, here this one. See, so look at this side, S naught less than dKs over mu max plus dKs, you get all trivial solutions, and this one you get trivial or non-trivial solutions depending on d greater than mu max or d less than mu max. Now, d greater than mu max is not possible, just as I explained, because d equals mu. So, and mu equals mu max times some number which is less than 1. So, obviously, d has to be less than mu max. So, that in that region alone you can get a non-trivial solution, fine. Okay. So, let us work through this. All we need to do is actually find the criteria. So, this is we understand this, that S naught has to be greater than dKs over mu max plus dKs. Now, let us consider the case of sterile feed. Why do we consider that? Just to make our calculations a little simpler. Sterile feed means X naught equals 0. Okay. Now, so again we are looking in the region of d less than mu max and S naught less than dKs over mu max plus Ks. So, in that region the SSS that you get is given by dKs over mu max plus dKs, okay. That is what we got last time. And if you go back and put these values into your the value that we got into your A matrix. So, A matrix is here. So, if you go and put these values, this becomes 0. Why? Because mu equals d. So, this becomes 0 and the rest of them are all non-zero numbers. Okay. So, that is the only term that becomes 0, but by becoming 0 it makes a calculation quite simple, because as you say this B2 will be simply minus A12 times A21 and B1 will be simply minus A22. Is it clear? Because A11 is 0, so B1 will simply be minus A22 and B2 will simply be minus A12 A21. Okay. Okay. So, this is my A matrix. So, over here sorry, I think I looked at, yeah, this is my A matrix over here, this term being 0. So, A11 being 0. So, all I need to do is prove that have my A22 to be less than 0, okay, because B1 is minus of A22 now, and what else I need? I need A12 times A21, the negative of that greater than 0, or in other words A12 times A21 less than 0. Okay. So, my two criteria B1 greater than 0 and B2 greater than 0, that is the two coefficients greater than 0, translate to, because A11 is 0, just I explained just now, translate to A22 less than 0 and A12 A21 less than 0. Okay. That is all. So, that would be, that is my criteria for steady state, a stable steady state. Now, A22 is this number over here, as you can see. Okay. So, minus A22 is minus of this number, Okay. So, this number d is positive number. Okay. So, del mu del s is what is it? Positive. I just explained why. So, this is a positive number, right. This whole thing is a positive, d is positive, del mu del s is positive, obviously x is positive and y is positive. So, this whole thing put together is a negative number. So, this is automatically satisfied. Is it clear? So, A22 less than 0 is automatically satisfied. Now, the other criteria is the only one that we have to take care of. So, this is a product of these two minus A12 times A21. So, d what you will get is d times xss over del mu del s over y, okay, and minus of that, and there is a minus out here. So, the whole thing comes out to be positive. So, d xss del mu del s over y has to be greater than 0. So, that is my criteria, okay, for greater than 0. I think I will come back to that. Okay. I think I do not have written it here clearly. So, basically my criteria for d less than mu max is simply del mu del s times d times xss times ys. Now, you got to tell me that less greater than 0. So, you got to tell me, is that correct or not? Does that hold? Is it stable or not? The answer is yes, it is stable, but why? We do not have to satisfy anything, it is automatically satisfied, everything is automatically satisfied for this criteria. Why? Because just from this, let me here, just because of this, del mu del s is this number mu max ks over ks plus s square, which is positive for all values of s. So, automatically, is that clear, or do I need to explain? Do I need to explain? Okay, just quickly through here. So, here A12 times A21, negative of that is xss del mu del s times d over x y. Fine. Now, d is positive, x is positive, y is positive, and del mu del s is positive. So, obviously, this whole thing is positive, right. So, this criteria is satisfied. Look over here, you have A22, this number has to be less than 0. So, this is positive, this is positive, this is positive, this is positive. So, obviously, the negative of the whole thing is negative. So, this is also satisfied automatically. Clear? Okay. So, both criteria automatically satisfied, as a result this condition is steady state is stable. The next one is the trivial state, as I explained that, you know. So, d greater than mu max, obviously you do not have anything but the trivial solution, but we are still looking at the stability of it, and the reason we are still looking at it, the stability of it, is because whether the trivial state itself is stable. You know, you can have a trivial state means what? That nothing really happens, you let the thing go in and it just goes out. But even is that stable, or that does that degenerate to some other unstable steady state? So, we are trying to look at that, and the A matrix here is slightly different because this d is no longer equals mu. Okay. So, this term is not 0. On the other hand, this term turns out to be 0 when you go and do the algebra yourself, but I am not going into the details of this one because this is a trivial state, but still. So, you get that A11 plus A22 when you add these two up equals this number, which is less than 0. Why is that less than 0? Because d is greater than mu max. Okay. So, if d is greater than mu max, obviously 2d is greater than mu max, 2d is greater than mu. So, therefore, this number is less than 0. So, it is satisfied, this criteria is satisfied, and the second one is A11 times A22 minus this term, this is 0. So, this product of these two have to be greater than 0. Okay. So, this criteria again is satisfied because d is greater than mu, d is greater than mu max, therefore, it is greater than mu. So, this is positive, the product is positive. So, what we figured out is that the trivial steady state is also stable. Okay. So, both criteria are satisfied and both lambdas are negative. So, the trivial steady state is also stable. Okay. Is that clear to all of you, or do you want me to repeat any parts of it? Okay. I am going a little fast because I want to finish some things. Okay. So, the next thing that we are going to do today is that apply the same calculations and the same process and the same mechanism that we did to multiple steady states and the case of substrate inhibition. Now, if I do not know if you have forgotten, let me remind you. So, this was what the case of substrate inhibition was. So, till now we did the monogrowth model with a simple thing. Now, you know, as I said that we did the case of multiple substrates, and similar kind of multiple substrates, what we get is this is my mu. Okay. So, we can do a similar kind of analysis using multiple substrates. The one that I am doing is the case of substrate inhibition. So, the reaction for that substrate inhibition was X plus S giving XS, and XS reacts with S again to give XS2, which does not produce new cells. So, if you remember, these were all the derivations, let me not go through them. This xt was the sum of the 3 x plus xs plus xs2, and then we went through this, and this is what we found. Okay. So, why are we interested in this? Because this is the only thing that is different from the previous case, okay, the value of mu itself, because everything, the balance equations, the rest of the analysis, everything is same. So, and if you remember, the reason we did it in the previous classes, we went up and did all the analysis without putting in any value of mu at all. The reason we did that is because the basic equations, irrespective of the form of mu, are the same, right. So, whatever form of mu we take, be it substrate inhibition, be it multiple substrates, other kinds of inhibitors, that is not a problem at all. We can just put in that form, everything into that form. So, let us go back here. So, you see, so this is my form of mu, which is mu max S 1 plus k s plus this term, apart from the monode, you have this extra term of S square over k I k s. Okay. So, what do you think, so these are not important for us. So, what do you think, in a way it is, because you see that del mu del S could be 0, but we will come to that later. So, what do you think, if I ask you that, so these are my basic equations, what would be the effect of substrate inhibition on the system? What do you think would be the effect? Huh? Screen, okay, yeah. What do you think would be the effect of substrate inhibition? These equations are written for sterile feed, I have written it down there. What we got last time, let's review. What we got last time without the substrate inhibition is that there is one trivial state and one non-trivial state, and both are stable. That is what we found, right? If I do a quick review. So, first question is two questions. What do you think in terms of what you will get in terms of trivial states and non-trivial states? A, and B is that what would you think about their stability? Just some intuition. We will work out the whole thing, whole maths in the rest of the class, but just some intuition.
Multiple states with some stable and some unstable.
Yeah, multiple states in a way. Last time also you had multiple states because you had a trivial state and a non-trivial state. Okay, so two states that were still multiple. But what do you mean by multiple states here? How many states? I mean, that is should be an easy answer, because what happens to the order of the equation? Order of the equation increases by one order of magnitude in S. So, from 2 to 3. So, how many 3? Yeah. So, that is a straight answer. For a second order, last time you had a second order equation, you got two steady states. This time I have a cubic equation. So, obviously, you are going to have 3 steady states. So, that is one part of the answer, and the other part obviously you cannot tell without doing the analysis, but what can you tell, what does your intuition tell you? What happens when there are 3 states?
So, the middle one is unstable.
Yes. So, let me show you this. I think I have drawn this diagram several times before. So, let us say this is X conversion, just like here, something like this, and this is the reactor Damkohler number, okay, which depends on the residence time of the chemostat, exactly the same thing. So, this is how it is going to be. Okay. So, these are, what are these called? I have told you this before. Still, what are the names mathematically of this? Limit points. Okay. They may or may not be ignition or extinction, depends on the catalyst and stuff like that, if you are doing a chemical reaction, but in mathematically the generic term for these is limit points. Okay. So, why are these words important is because there is between these limit points, okay, in this region of these limit points you have 3 solutions, okay, and beyond that 1 solution and 1 solution. Okay. So, between this only you have the cubic solution. What it means is that when we solve it, you will see that outside a certain range in the of the parameter, there is a single solution, because the determinant goes off, determinant goes to 0 or something like that. Typically the determinant goes to 0 on the outside range, and you end up with a single solution, and within that you have just 3 solutions. So, if I look here, if I look at the stuff again. So, so limit points these two, and this is a, so this is the ignited branch, this is a stable solution, okay. This is a unstable solution, okay. And sorry, this is unstable solution, the middle one, and this is a stable solution, okay. So, the bottom branch is a stable solution, the top branch is a stable solution, and the middle branch is an unstable solution. Why is it unstable? Is because if you for some reason go into the unstable branch and allow the system to stay there, it will either go to the top branch or the ignited branch, or go to the bottom branch or the extinguished branch, depending on whichever is closer to it. Okay. It does not stay there for very long. So, your aim is never to operate close to the stable unstable branch, and how do you ensure that? If as an engineer, for example, if you are to operate your plant or your reactor in a certain parameter range means say residence time or liquid volume or the substrate concentration, whatever it is. Okay. How will you ensure that? How will you ensure that it does not go to the unstable branch? You choose your parameter such that it does not go to the unstable branch, right? How do you choose? How do you choose your parameter such that it does not go to the unstable branch? Yeah, but there is a procedure for that, and that is called, let me see if you have heard of this, neutral stability analysis, okay, and that is exactly what we are doing now. Okay. What is this? Basically, it draws, you essentially draw this in the parametric plane. For example, see here it could be in the plane of Damkohler number versus Peclet number, something like that, or Peclet number here, let us say Peclet number here and Damkohler number here. Then what it gives you? It gives you a curve like this. Because from here this diagram that I drew, how do you know? You never know. For otherwise, what you have to do, you have to choose every Damkohler number, go and make some simulations, find out whether your solution is in the stable branch or unstable branch. That is a complete waste of your time. You can't keep doing it. So, what you need to do is you need to isolate or figure out in the parametric plane of Peclet versus Damkohler what is going to be whether the system is going to be stable or unstable. So, this is a branch part where it is going to be unstable and the system is stable here, which means that you choose your parameter such that it stays within this range, okay. It stays within this stable part. It could be the other way around also, it could be that inside is stable, outside it is unstable, very unlikely, but typically because as Peclet increases it becomes unstable. So, but there is a possibility that it can happen, stable can be inside, unstable can be outside. So, our aim to do this, our engineering aim to do all this analysis is to be able to come up with this neutral stability diagram, so that we do not have to do the calculations every time. We can figure out in the parametric space what part is stable and what part is unstable. As a result, as soon as you as soon as you in the reactor, as soon as you choose your parameters, your flow rate. So, Damkohler and Peclet number, between them contain all the parameters essentially, flow rate, volume of the reactor, reaction time, the size of the the diffusion length scale in the reactor, the diffusion coefficient of the species in the reactor. So, all these parameters are contained between the Peclet and the Damkohler number. So, if you look here, so essentially that you choose your Peclet and Damkohler such that your system stays here or here or here and does not go here, anywhere here. Okay. So, that is your aim. So, you can directly choose the parameters, you do not have to do calculations all the time. Once you get the stability neutral stability curve, this curve once and for all, you can directly choose your parameters and make sure that it is in the stable branch. So, that is our aim, not to just solve one problem, not to just solve for the steady states and analyze the stability of the steady states, but to get a neutral stability curve, so that you can use that at all times. Okay. So, that is what we are trying to do over here. So, as I discussed, that this being a cubic equation, this will have 3 solutions, okay? And out of these 3 solutions, it turns out one will be a trivial solution and the 2 would be non-trivial solutions. Okay. So, then we have to look at the stability of these solutions. So, the trivial solution, as we had looked before, is simply going to be XSS equals 0 and SSS equals S naught. And the non-trivial solutions, if you solve these, so how do I solve this? Remember what we did was we did a invariance, right? We did an invariance. So, you multiply this by this second equation by y and add these two up, and as a result this term will go, then you can express s as a function, x as a function of s, and then you put it back over here and then solve it. So, you solve it by the method of invariance, and this is what you get. This is only, remind you, valid for mu max greater than d. Okay. This is mu max not equal to d, rather this is valid for mu max not equals to d. Why is it valid for mu max not equals d? Because for mu max equals d, what will happen is this quadratic form. Remember that you have taken out the trivial solution. So, you had a cubic equation to start with, you take out one of the solutions, which is a trivial solution, then you have a quadratic form. So, this is a quadratic form you are solving. So, if this thing is like s, so the cubic form will be some s times a1 s square plus a2 s plus a3 equals 0. So, this is the form once you put that. So, this will give you the sorry, this is not s minus s naught. So, this is so this will this part, the trivial solution, this is trivial, will give you s minus s equals s naught, and this is the non-trivial part. So, this is a quadratic you can solve, but what I am trying to say is that a1 equals mu max minus d. Okay. A1 equals mu max minus d. So, what you need to do is when mu max equals d, then you need to drop this completely from the equation itself. Do not solve the quadratic and then try to fiddle around, because it will come in the denominator or something, then the whole thing will blow up. So, if mu max equals d, then just drop this term completely, and then you have a linear and you have just one single solution, which is given here. So, so this solution over here is for mu max for a1 equals 0, then this is given by k1 ks. Okay. So, if I can go back to the screen now. So, the non-trivial solution is given by SS equals 2 ki over ki over 2 kd, this term mu max minus d plus minus this determinant. Okay. And XSS, so this is my SS, and XSS is obtained as S naught minus SS times y, okay, because this is from material balance, right. So, if S naught minus S has been consumed, then y times that would give you the amount of cells that has been formed. So, for mu, as I said, for a1 equals 0, the first coefficient equals 0, or for d equals mu max, SSS is square root of ks over ki. Okay. So, the two solutions that you get over here, these two, the non-trivial solutions, provided that mu max minus d is greater than this, or in other words, the determinant, the discriminant is greater than 0, its discriminant is positive. Okay. So, you get this. So, mu max minus d 2 kd, is it correct? Okay. So, now what we have, so these are essentially my 3 states, okay, 3 states. For the special case where mu max equals d, I have this state, but apart from that, essentially for all other cases, these are my 3 states. Now, what I have to do is I have to look at the stability of the 3 states. Predictably, your trivial state is going to be stable, predictably, but we will still have to, we will still check that. So, what is my difference that I need to do? Everything is same as again as before, only my mu is different. So, I need to calculate my del mu del s. Okay. Now, what do you suspect in terms of the stability? We have looked at the 3 states. What do you suspect in terms of the stability of the states? something, yeah, I think you told Arush already said that one of the solutions is going to be unstable and the other two are going to be stable. Yes, that's what I also suspect, but can you sort of intuit the reason for that? Okay, if you're kind of, what could be the reason for that? What was the driving force the last time we did for the normal case? What was the driving force behind making these solutions stable? Both the solutions it turned out were stable, but what was the driving force? What is the reason for that?
D was greater than mu max.
No, D has to be always greater than mu max for a solution, a feasible solution to exist. If D is not greater than mu max, it's not going to work.
Del mu del S was.
Yeah, correct. The reason behind that was del mu del S was always positive. But if you remember from the last time what we did in our growth model, del mu del S was not always positive. It's positive, goes to 0 and then decreases, right? Okay, if you remember. So that is the reason why. So in the region where del mu del S is not, so it turned out that if del mu del S were not positive last time, for example, then the system would be unstable. So what we can predict or intuit, I mean, it's not mandatory that exactly mathematically we get, but we have to always couple some kind of intuition with your mathematics. So what we intuit is that for the region where the specific growth rate decreases with substrate, the system is going to be unstable. And physically, if you think of it, it makes sense that if this if you are increasing the amount of substrate, but the specific growth rate is decreasing, that is a really worrying case, right? Physically speaking, and that probably is the region where there are sources of instabilities. Okay. So, let us try and look at it. So, this is my mu, the first thing you say is mu over here with the excuse me, the inhibition term in there, and this is my del mu del S or d mu ds over here, and which could be negative or positive depending on the numerator, because the denominator is always positive. It is the numerator which can go negative or positive. So, depending on whether S is greater than square root of k I k s or less than square root of k I k s, then you have trouble. Now, if S equals square root of k I k s, then you have the, what do you have? Not the trivial solution, no, trivial solution is 0, this is the solution, d equals mu max and S equals S square root of k s, k s k s. Trivial solution is this one, let us not confuse trivial solution with this. This is this trivial solution, these are non-trivial solutions. A special case of the non-trivial solution is this one where d equals mu max. Is it clear, Lisa? If there is any problem, I understand this is probably the hardest thing we have done in this till now, but if there is a problem, just stop me. And so, the special case of the non-trivial solution is S square root equals square root of k I k s, but in general we have the trivial solution and two non-trivial solutions. Okay. So, out of the trivial, so the trivial solution, out of the non-trivial solution, there is one possibility of S being equal to k I k s, in which case del mu del S would equal 0, right. That is one possibility, but that is a exceptional possibility, a special case, but in general k s k I would have to be greater than 0 or less than 0. So, depending on whether it is greater than 0, so sorry, k I k s is not greater than 0, sorry, greater than square root of k I k s greater than S or square root of k I k s less than S. So, if square root of k I k s is greater than S, then we probably think that the system is going to be stable, fine. Okay. So, so we consider the non-trivial states over here, and for the non-trivial states the mu equals d. For the trivial state it is not necessary, but for the non-trivial state mu equals d, right. If you remember, we had x times mu minus d equals 0. Okay. So, for trivial state this is x equals 0, for non-trivial state mu equals d, right, because these are things you have to remember as you do this. So, so this matrix A that we have, this is the same matrix that we have, remember, exactly same as what we did last time, okay, because we still have a generalized form of mu, we have not put in our mu into it. So, now we are going to put in our mu into it. So, our stability criteria was A11 plus A22 less than 0, or in other words this term to be negative, okay, and the other one is A11 A22 minus A21 A12 greater than 0, and in other words the product of these two terms to be positive. Now, to remind you again, the last time we had an advantage because del mu del s was greater than 0. So, we could conclude directly that yes, if del mu del s is 0, then greater than 0 is positive, then of course, this whole term is going to be negative. Similarly, if del mu del s is positive, then of course, the product of these two terms is going to be greater than 0, right. Is it clear to everybody? Okay. So, this we could conclude that directly. Now, we cannot conclude that directly, and we have to depend on a case by case basis. So, this is my criteria now. So, del mu del s times x over y plus d should be greater than 0, and this one will lead to del mu del s times dx over y should be greater than 0, fine. Now, for del mu del s to be greater than 0, my s square, as I just showed, s square has to be less than k I k s. Okay. S square has to be less than k I k s. Okay. So, that is my stability criteria essentially, that S has to be less than, and this is what we had intuited, just by looking at the equation itself we had intuited this. So, my stability criteria is that S has to be less than square root of k I k s, and you can go back and check all rest of it, you can put over here, you can do the rest. I have skipped that calculation, but you can do you can differentiate, the differentiation is already there, you can go and put this back over here, but it is very, coming back to this model, one of the things you need to, though I don't kind of ask you, I mean I am not suggesting that you do that in the exam. I want you to put the stability criteria A11 plus A22 greater than less than 0, and the other two terms A11 minus A22 minus A12 A21 greater than 0, and then come through it. But at the end of the day, if you come to think of it, what is your stability criteria is essentially coming down to del mu del s should be greater than 0, right. Is that correct? You do all the calculations, and I do not suggest that you do not do the calculations in the test or something. You do the calculations to show that you know everything and this is the proper way, but a check on your calculation essentially would be what to find out what is my criteria such that del mu del s is positive. So, at the end of the day, that is what matters, but then again do not go and write it straight away, okay, derive it. So, this what you see on the screen is now my neutral stability curve, okay, the thing that I have been trying to get. And look what I have over here is that S naught over D. So, this is a major difference between what I showed you, that a multiple solution curve, that is called known as a bifurcation diagram, okay, the one that I just showed you over here, this one, if I can go to the paper, okay. Yeah, so this is my bifurcation diagram, and my neutral stability curve would be this. Okay. Now, I need to draw a fresh diagram and of the bifurcation curve and the neutral stability curve together, and there is something I want you to help me with. So, as you can see that this extinguished branch essentially saturates, over time it kind of saturates over Damkohler number, it saturates, let us say this is Damkohler and this is the conversion X. Now, I want you to tell me, help me with how the neutral stability curve is going to look like. So, this is my bifurcation diagram. I want you to help me with how my neutral stability curve would look like. How would it look like? It would have a state, it would look similar to what I told you, like right this, okay, what I drew over here. But where would they be? How would I place that? So, let us say my neutral stability curve in again x axis is still dA, but y axis is Beckley. Do you understand, do you discern the difference in terms of the axis for the bifurcation and the neutral stability curve? The major difference is that bifurcation curve is drawn in the variable space, neutral stability curve is drawn in the parameter space. Okay. So, this is the variable space and this is drawn in the parameter space. And there is, so variable space means one's variable versus a parameter. There is this is in the parameter space, which means 2 parameters, and then there is another kind of plot, what is it called, where 2 variables you have and you draw one variable versus another. For let us say in this case, if I want to draw in the x versus s space, what is it called? What is it? You don't remember, who remembers? It is called the phase space. Okay. So, if the variable space here, the parameter space here, and the phase space is where both the variables are drawn against each other. Okay. And so this is something that is important and you to understand, that although I explained it before, that you necessarily draw the neutral stability curve in the parameter space and not in the variable space or the phase space. The reason you do that is because you are not interested in what the value of the, do you understand what I am trying to say? You are not interested in what the value of the parameter variable is going to be, you are interested in what parameter should you operate your reactor in. Okay. You are not interested whether x is going to be 0.9 or 0.8 or 0.7 or 0.6, that is not your concern. You are not even interested whether it is going to be ignited or extinguished. That is an important question, by the way, that if you look at this bifurcation diagram over here, this is the ignited branch and this is an extinguished branch. It is important actually to figure out whether the system is going to operate in the ignited branch or the extinguished branch. Why? Because you want it to operate in the ignited branch, yes, because you want product, you won't run a reactor without generating product. So, if you are in the extinguished branch, you hardly generate any product. So, that is important, but more important than that is whether the system is stable or unstable. Okay. So, that is why the more important thing is the neutral stability curve. First comes stability. Once the system is stable, then you worry about whether you are generating enough product or not enough product. Do you understand what I am trying to say? The first is stability. So, once the system is stable, there are two possibilities, that the system could be in the ignited branch or in the extinguished branch. If you look over here, as we discussed, that this leg, the bottom leg is stable, the top leg is stable, but the middle leg is unstable. So, even when the system is stable, there is still a possibility of it being in the ignited branch or in the extinguished branch, and you want it in the ignited branch, right. So, I will come to that also, how to figure that out, but your first criteria is stability. So, now you tell me that I have explained so much, now you tell me that how do I draw my neutral stability curve?
Between the limit points.
Between, good, yeah, between the limit points. So, this is how it is. You draw a line over here and a line over here, and your neutral stability curve will be like this, and then this. Okay. So, this is the system is unstable over here and stable over here. Okay. So, this corresponds to this branch, corresponds to this. Okay. This branch over here corresponds to this branch corresponds to this, and the middle branch corresponds to this. Okay. So, the two limit points correspond to the two horizontal. So, two limit points correspond to the two vertical limbs. Please remember this always. So, the two limit points correspond to the two vertical limbs of the neutral stability curve. Okay. So, now my problem is solved. So, I now know that what part is stable and what part is unstable. I can choose my criteria such that it is stable. Now, how do I choose whether it goes to the steady state, to the ignited state or the extinguished state? That also I can choose from the neutral stability curve. If you look here, okay. So, if I choose something around this point, then it will be in the ignited state. Okay. Just say after this vertical, second vertical limb. Okay. So, it will go to the ignited state. If I choose something out here in the towards my left hand corner, complete left hand corner, then it will go to the extinguished state. So, I want my two things. I want my system to be stable, I want it to have attained maximum, to give maximum product. So, which means that first it has to be either on the ignited and the extinguished branch, and second would be it should be in the ignited branch. So, so this neutral stability curve is a very useful thing in a way, because it lets me choose my parameters, my flow rate, my reactor size, my reaction rate, my diffusion coefficient, everything, such that say I choose something like this would be probably the optimum choice, because it makes sure that it is stable, or you can go here, make sure it is stable and make sure it is in the ignited branch. Okay. Is that clear to all of you? Okay. Now, let us go back to the screen. So, this was a generic thing that I showed and this is the actual thing. So, this is the washout case, or in other words this is the trivial solution. Trivial solution means that no product is being formed. So, we are not really worried about this, and this is my how my neutral stability curve looks like, and there is a essentially vertical limb also, it goes up a little bit. So, sometimes it is a little sharp, sometimes it is kind of flattened, all these things happen, but you go a little up and then it kind of sharpens out. So, this is my unstable solution is middle in the inside here above, and the rest of the system is stable solution. Okay. What is this line over here? This line is not properly drawn, actually it should touch this this blue line over here. So, anyhow this line over here corresponds to, it is written here, the steady state value of the substrate. Okay. So, this is not a part of the, let me not confuse you any which way. This is this line, blue line, this blue line over here is the bottom line, this one is not a part of the neutral stability curve. Okay. It is just a concentration plot or substrate plot relating to this value. So, do not worry about so much about this line, just worry about this one. So, this is my neutral stability curve, and as we concluded that the system goes unstable not just with multiple inhibition, in general the system goes unstable well when del mu del s is negative, and then it end up having positive real roots. So, for del mu del s negative, this is the part, the unstable solution, and for del mu del s positive, everything here below is stable. So, this is my your neutral. I probably suspect that this is your first encounter with neutral stability curves, right. So, just want to make sure that everybody understands. If there is any question on neutral stability curve, you can ask me now or maybe a minute later also. So, yeah, I think these are, yeah, this is a overall neutral stability curve, and this is the details of the calculation that I skipped, all the calculations, I skipped. You can go through these calculations. Do you want me to go through, or just not very, it's kind of trivial. So, essentially the way I skipped the calculation is because I just showed that del mu del s greater than 0 is stable. So, but this is the hard way, going through all the details and everything. So, this is a better picture now I have of this unstable, and this so this is in this is taken from somewhere. So, these are rates in gram per liter and D. So, what essentially it tells me, if you look at this neutral stability curve, if I want to be in the stable region, then it gives me numbers on two of the parameters. One is the S naught, the initial substrate concentration I use, and the second one is the D, or the inverse of the residence time. D is the inverse of the residence time, or in other words residence time itself. So, what it tells me is that what should be the size of the reactor, or size cum flow rate. So, residence time is ratio of these two, A, and B would be what would be my initial substrate concentration. This is what it tells me. So, that I can pick. So, if you look at the curve here, so I can pick any point over here. For example, I pick a point over here, a point over here, so that the system is stable, and I know that for my S naught, for the system to be stable, for my S naught to be if my S naught is this, my dilution rate has to be this, or in other case, if my reactor is given to me, okay, I cannot make changes to its flow rate and its size, then I pick my S naught, initial substrate concentration, such that it is in the stable zone. Okay. So, if you need, you can go through the calculations on your own. So, these are these calculations you can just, if you need to feel comfortable with it, you can go, as I told you, there is this state 1s is outside the quadratic. So, these are the values, mu max is our inverse. So, these values are in a way important if you actually want to plot it. So, as you can see that the reaction mu max is sort of gives you the reaction rate, and that is of the order of hours. And so, dilution rate, this is not 0.6125, 0 point, it should be 0.6125. The dilution rate is also of the order of our inverse, and you ensure that D is less than mu max over here, right. So, D is less than mu max, that is ensured, number 1, and number 2, they are of the same order and they follow the stability criteria. Okay. So, that in a way concludes our discussion on stability of these states. Now, what maybe some assignments you might want to do on your own is that these stability criteria that I show over here is for the inhibition, but let us go back to this just a sec. I don't know what's happening. Let us see. Yeah. So, this stability criteria that you obtained over here is for all possible values of mu. So, some of the things that you might want to do is look at how you change your mu and that how it changes the stability of the system. Now, it may be a little boring to do that to start with because of the maths, but once you go through the maths and you essentially will come out, and one of the things you might want to tell me is that whether our intuition that for all del mu del s greater than less than 0 is the system unstable. That is the question I pose to you. Okay. For different if I go to this one, let us say, yeah, here. So, system like this, okay. For all kinds of del mu del s less than 0 is a system unstable, this system or any other system, any other kind of growth models. We had huge, I mean a lot of different growth models we have studied, if I remember. Just a sec. Yeah. So, the monod, Malthusian, logistics, all these different growth models are here. So, one question A that I pose to you is that are all these growth models, for all these growth models is the system unstable for del mu del s less than 0, A. And B is that even if it is unstable, what kind of solution space you get, what kind of neutral stability curves in the parametric space that you get. And this is something that you might want to look at in your at home or something like that, and it's important to be able to, because we just did these two particular cases, the growth model. One of the things, easy things you can do is simply do the modified monod growth model, which is very straightforward, same as the monod growth model almost, because there is not much effect except for that K is not here. But if you take this model for example, how does it change your whole system, and how does it change the neutral stability curve and the neutral stability space? The reason I am talking about this is, see, till the point we write the basic equations for the system and keep any mu out there and do our analysis, it is all valid. But you have to realize that the growth model, when we put in, is an artificial thing. Do you understand what I am trying to say? The growth model itself is an artificial thing. The balance equations with any mu in there is a real thing, okay, because things are happening that way, but the growth model is an artificial thing. So, it could be that I can choose growth model number 1 and you can choose growth model number 2 for the system, and we should not come up with wholly different criteria for neutral stability. Do you understand what I am saying? Because at the end of the day, irrespective of what engineer number 1 chooses a growth model and engineer number 2 chooses a different growth model, the system should still run. So, you might want to check with different kind of growth models and try and see that whether the neutral stability curves that you get is similar or different. Okay. So, we will stop here, and tomorrow's lecture, I think, are there any questions on neutral stability? If there is, what you might want to do is think about it and ask me at the beginning of the class, next class. That is one possibility. I think because this is probably one of the hardest things we did, this calculations and everything in this course. So, is there anything you want to ask at this point on neutral stability, or let's save it for tomorrow? Okay, so we'll save it for tomorrow. If there is any question, I'll stop. Maybe towards the end of next lecture, we'll spare a few minutes and go through, and we'll start a new chapter in the next class. Okay, thanks.